In single variable calculus, one method that we learned to evaluate integrals was the method of substitution. This was a method that allowed us to look at an integral of a composition of functions, say f of g of u times some g prime of u. And what we did was we made a change of the variables. We let x be a function of u, x equals g of u. And then dx, by the chain rule, would be g prime of u du. This allowed us to evaluate a much simpler integral, an integral of f of x dx. But instead of the limits of integration going from u equals a to u equals b, they went from x equals c, which was g of a, to x equals d, which is g of b. So in essence, what we did was we changed this very complicated integral of f of g of u, which is a function of u, to a more simple function of x. So we've changed the variable from u to x. We would like to do something very similar in multiple dimensions, working with double and triple integrals. But as you will see in this video and the next, we'll actually be working in reverse, where we're going to take an integral of something simple like f of x dx over a really complicated domain, and then we're going to change the variables so that instead we're going to work with an integral of f of g of u times g prime of u du. Before we can get into how this change of variables is going to work, we first need to look at transformations on the plane. So previously, we've looked at functions that input a vector and output a number. So they input multiple variables and output a single number. We've also looked at functions that input a single number and then they output a vector, like parameterizing a curve. Now we're going to look at a new type of function that both inputs and outputs a vector. We're going to call that function a map. In this case, we're going to let that map input a vector in R2 and output a vector also in R2. So the input and the outputs are both vectors. So let's define a map T, which takes in variables u and v and then outputs an x and a y. And we're going to define it by the functions x equals f of uv and y equals g of uv. So in essence, we're going to output a vector x, y, and that output vector is going to be given by f of uv comma g of uv. And then what we want to do is we want to look at a region in R2, we'll call it S, and what we're interested in knowing is what is the image of S under the transformation T? In other words, what is T of S, the set of all points that can be written as T of uv, where u and v is in S. So we're going to take some region in our plane R2, and then we're going to apply the function T to all the points in that region, and then we want to see what is the resulting set of points. What is the image? This is best illustrated by an example. So I'm going to find the image of the following transformations T that take an S and output something in the plane. So what we're going to do is we're going to start with a T of uv, and that T of uv is going to be given by x being u plus v over 2 and y being u minus v over 2. And then what we want to do is we want to run x between minus 1 and 1 and y between minus 1 and 1. So we're going to have a square in the uv plane, And we want to know the image of those points in the UV or in the XY plane. The way that we're going to do this is I'm going to look at what happens to the boundary of this square and see where the boundary ends up when we apply our map T. So we're imagining that we're taking this square and then we're mapping it to something in the XY plane via this transformation we're going to call T. So I'm going to start by looking at along this boundary, along the boundary where u equals 1. So here we're going to take T and we're going to apply it to when u equals 1, but V is just going to stay V. And so I want to know what happens in X and Y. Well, X is going to be 1 plus V, because u is 1, over 2. And then Y is going to be 1 minus V over 2. So I want to understand what line is going to appear in the XY plane. So I want to establish a relationship between X and Y. So I'm going to look at what happens with X plus Y. If I add X and Y, I hope that you notice that the V's cancel. And what's left is a half plus a half, which gives me 1. And so I can think about this as being the line y equals 1 minus x. And so this blue line, along which u equals 1, it transforms to the line y equals 1 minus x. And it's going to be that line segment, because I'm going to be interested in what happens at the various points. So at this point, this is going to be t. I'm going to apply that. I want to apply t to the point 1, negative 1. And so t of 1, negative 1 is going to be, if I plug in 1 and negative 1 for u and v, then I'm going to get that the first component, x, is going to be 0, and then the second component is going to be 1. Okay, so this point 1, negative 1, okay, it goes to the point 0, 1. And then I'd be curious, okay, what happens to the point here, 1, 1? So I'm going to apply t to 1, 1. And what I'm going to get when I plug in 1 and 1 for u and v is the point 1, 0. So that's t of 1, 1. So if I move up along this line segment, then I'm going to move diagonally downward along this line segment here. Okay, that gives me the first line segment. The next one that I'm going to do is when v equals 1. So I'm going to move along this line segment. So there I want to look at what happens when I do t of u comma 1. Now t of u comma 1, that's going to be u plus 1 over 2, and then u minus 1 over 2. And then I will notice that if I take x and subtract y, then that will make the u's cancel. So if I do x minus y, the u's will cancel, and what I'm left with is going to be 2 over 2, or 1. And so here I'm going to have that y is going to be x minus 1. So I can take the line segment where v equals 1, and that ends up being the line segment where y equals x minus 1. Now we already know that it's 1, 1 starts at this point here. So I just need to figure out what is the image of this point here. This is negative 1, 1. So t of negative 1, 1, if I plug in negative 1 and 1, u plus v is going to be 0. So the first component is going to be 0. And then when I do u minus v, I'm going to get negative 1 minus 1 gives me a negative 2 over 2 or a negative 1. Okay, so that's going to get me to the point there. So the red line segment ends up mapping there. Okay, now let's do a third line segment. That's where we're going to have u be negative 1. So if I let u be negative 1, so I'm going to do t of negative 1 comma v, and that's going to give me u is negative 1, so that's going to give me negative 1 plus v over 2, and then negative 1 minus v over 2. I'll notice that if I add x and y together, that will cancel out the v's, and that will give me a negative 1. So that will tell me that y is equal to negative x minus 1. So I can then plot this line segment. Okay, this is the line segment y equals negative x minus 1. And I already know what happens at the corner t of negative 1, 1. Okay, so now I'm just curious what's going to happen at this corner, negative 1, negative 1. And so t of negative 1, negative 1 is going to equal, well, the result is going to be negative 1, 0. So it takes me to that point. So I'll move along this line segment. Okay, finally, let's do the last line segment. Okay, what happens when I do t to this line where v is equal to negative 1? Third time's going to be the charm here. Okay, t of, we're going to do u negative 1. So that's going to be u minus 1 over 2, and then u plus 1 over 2. And then again, if we combine x minus y, then we'll eliminate the u's, and what's going to be left is going to be just negative 1. So this gives me the line segment y equals x plus 1. That is this line segment. And so if we move along this direction, we'll end up moving this direction. Okay, so what happened with this square is when we applied t to this square, the result was a diamond. Okay, so it's pretty easy to see that the point 0, 0 does map to 0, 0. So it does map to t here of 0, 0, which is 0, 0. And so essentially the interior of this square is going to map to the interior of the diamond. Okay, so we've now shown that if we want the image of S, it is in fact going to be the interior and exterior of this diamond, which we'll call T. And that gives you a sense of how you can find the image of various transformations. I want to do a much simpler transformation. This is one that we might be familiar with. Okay, T of R and theta. Okay, so here R and theta are, R is going to be going from 0 to 1, and theta is going to go from 0 to 2 pi. And so we're going to take that rectangle S, and we're going to see what happens when we apply the transformation T, where we're going to let X be R cosine theta and Y be R sine theta. So I'm going to be curious what's going on along when R is equal to 1. Well, when r is equal to 1, then we're going to let theta go from 0 to 2 pi. So if r is equal to 1 and theta is equal to 0, we're at this point here. And then if we let theta trace out from 0 to 2 pi, what we get is the unit circle. So that, in fact, gets us the unit circle. And so our image of this rectangle from 0 to 1 in r and then 0 to 2 pi in theta is, in fact, the unit circle and then the interior of the unit circle. And so this is just the polar coordinate change that we have been familiar with from previous videos.